Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we'll demonstrate the testing process for our new multi-GPU parallel computing method. Previously, we reviewed the Fortran program and scripts that we'll be using for these tests. In our previous video, we mentioned increasing the memory allocation from 8 to 16 gigabytes. This adjustment accommodates the addition of the CR matrix in our Fortran program, alongside other matrices. While this increase in memory might be too much, it will not affect the billing factor. We can use our setup script for interactive jobs located in the error directory of my work folder to examine changes in the billing factor when we increase the memory request from 8 to 16 gigabytes. Currently, with 16 CPU cores and 2 GPUs, the billing factor for 8 gigabytes of memory is 16. Upon executing the setup script again, we find that the billing factor remains at 16 for a request of 16 gigabytes of memory, along with 16 CPU cores and 2 GPUs. We will execute the testing process as a batch job by submitting it with the sbatch command to the Slurm workload manager, and we see that the job is assigned the number 11805857. We can use the ll command to verify if the job has generated the Slurm output file. Once confirmed that the file is created, we can view it using the Emacs editor. The Slurm file contains some warnings and notes, which we can remove to enhance clarity. The wall time for multi-GPU parallel computing with 2 GPUs is approximately 17 seconds, achieving a performance of about 32 gigaflops. Previously, using one GPU, the wall time was about 22 seconds, resulting in a speedup of approximately 1.3 when upgrading from 1 to 2 GPUs. To verify the accuracy of the updated multi-GPU parallel computing method for matrix multiplication, we will execute the Fortran program one more time. This time, we will save the matrix C to a data file and use this file to confirm the correctness of the calculations. To submit our job to the Slurm workload manager, we use the sbatch command, which assigns it the job number 11805959. We can then use the ll command to verify that the job has created the data file, which we find to be over 7 gigabytes in size. Let's navigate to the error directory we created in a previous video and list its contents using the ll command. First, we need to rename the CData file to reflect that it was generated using our previous method, which incorrectly assumed shared memory among GPUs and did not utilize the reduced matrix CR. Similarly, we will rename the error data file. Next, we'll move the new CData file, created with our updated method for multi-GPU parallel computing, to the error directory. We can verify these changes with the ll command. After these changes, we execute our setup script to switch to a single CPU core on one compute node. We'll execute our Python error script. The script will display the compilation command. The Python script will execute the compiled Fortran program, which may take some time as it processes large matrices from the data files. Once the program completes and the command prompt returns, we can exit the compute node. We can use the ll command to check if the Fortran program created a data file named error. Next, we'll use the more command to inspect the number inside the data file. We can see that the number is 0, allowing us to conclude that our updated method, which utilizes the reduced matrix CR, correctly performs the matrix multiplication. In our Fortran program, we've chosen to split the matrix C over the J loop, the outermost index. Now, let's test splitting the C matrix over the I loop, the innermost index. I've created a Fortran program with the file ending 6, and for this test, we'll set n to 16384 and use 2 GPUs. In this program, we'll use IR instead of JR. We'll allocate the CR matrix with the reduced dimension on the innermost index. In the initialization loop for matrix CR, we'll use the IR and RN variables. In the matrix multiplication loop, we'll use the IR and RN variables, setting I equal to offset plus IR. Finally, we'll use the CR matrix to fill up the large C matrix. After adjusting the file ending to 6 in the Python testing script, we can submit our job to the Slurm workload manager using the sbatch command. We can then use Emacs to view the Slurm output file and observe that the wall time is similar to our previous test. This indicates that splitting the matrix C over the innermost or outermost index does not affect performance in multi-GPU parallel computing with our Fortran program for matrix multiplication. This happened because the two outermost loops, I and J, were combined into a single loop during GPU offloading. Let us now try with 4 GPUs, and thus we need to set the parameter for number of GPUs equal to 4 in the Fortran program. In the testing Python script, we must change the billing factor to 32. We submit our job to the Slurm workload manager using the sbatch command, which assigns it the job number 11806436. Using the sq command, short for show queue, we can see that our job has been executing for 3 seconds. After some time, we use the sq command again and observe that the job has completed. We can use the ll command to check if the Slurm output file for job number 11806436 has been generated. Once we confirm the file's creation, we can view it using the Emacs editor. In the Slurm output file, we observe that the test was conducted on the GPU 12.3 node. The file also includes some warnings and notes, which we can remove to improve clarity. The wall time for parallel multi-GPU computing using 4 GPUs is approximately 12 seconds, achieving a performance of about 23 gigaflops. Previously, with 2 GPUs, the wall time was around 17 seconds, resulting in a speedup of approximately 1.4 when upgrading from 2 to 4 GPUs. With 1 GPU, the wall time was about 22 seconds, leading to a speedup of approximately 1.8 when upgrading from 1 to 4 GPUs. Let us increase the matrix dimension to 32,768 and do one more test with 4 GPUs. In the testing GPU script, we must update the dimension to 32,768. In the job script, we change our memory request to 52 gigabytes. You might remember from our OpenACC on A-100 video that we used a memory request of 26 gigabytes. We are increasing the memory allocation for our Fortran program from 26 to 52 gigabytes to include the CR matrix. Although this may seem like a substantial increase, it will not impact the billing. Additionally, since we are utilizing all CPU cores and GPUs on a single A100 node, we can fully utilize the memory capacity on a single A100 node. We can submit the job to the Slurm Workload Manager using the sbatch command, and it has been assigned the job number 11982439. By using the SQ command, we can see that the job is currently pending while it waits for resources. Checking again after some time, the job status remains pending. We will verify the completion of the job tomorrow. After the job is completed, we can view the Slurm output file using Emacs. This file reveals that the test was conducted on the GPU 12.3 node. The file contains some warnings and notes, which can be removed for clarity. The initial outputs are details about the adjustments to an AMD architecture-compatible environment. Following this, the compiler provides some insights into OpenMP parallelization. The Python script used for testing also displays the full compilation command for reference. Utilizing multi-GPU parallel computing with 4 GPUs, the matrix multiplication was completed in approximately 68 seconds, achieving a performance of about 32 gigaflops. This can be compared to performance using OpenACC offloading. In our video OpenACC on A100, we achieved the best performance with a wall time of about 52 seconds using a single GPU. The job experienced a 9-day waiting period in the queue before execution, which is unfortunate but not uncommon due to the high demand for the A100 nodes on the Saga Linux cluster. However, we anticipate improvements soon with the introduction of the next supercomputer. This upcoming system will feature 76 nodes, each equipped with 4 Grace Hopper superchips. We have now demonstrated how to use OpenMP for both multi-threading and GPU offloading. In our next video, we will take multi-GPU parallel computing a step further by merging OpenMP multi-threading features with OpenACC offloading. This integration will enable us to explore the full potential of multi-GPU parallel computing using both OpenMP and OpenACC. I am looking forward to the next video, wishing you all happy computing in the meantime.